So Shih-Chii and I have been co-directing the sensors group at the Institute of Neuroinformatics here since we got here more than 20 years ago. And Professor Shih-Chii got her EE degree from MIT and her PhD as the very last student of Carver Mead. And Shih-Chii's silicon cochlea designs paved the path for all the recent mixed signal, ultra low power audio processing chips, and her seminal work on spike-based hardware processing for processing and fusing event sensor data anticipated later work by at least a decade. Her work has covered a very broad range from mixed signal CMOS to digital to deep learning, signal processing, cortical stimulation for blind people. She's a coordinator of a big cortical stimulation project now, and even sweat sensing. And today, she kindly agreed to present seminal work on sensor fusion of visual and audio events in a spiking deep belief network and its implementation in Minitaur, the first bona fide digital spiking accelerator that exploited sparse computing ideas. So go ahead, Shih-Chii, please.
Yes, I'm going to talk about fusing Cochlea and Retina events in deep belief network. And in particular, it's looking at the kind of representation that you get from this kind of sensors. And I think Toby showed you this before. So here, for example, is an example of what you would get from the silicon cochlea across the different frequency channels. And what you get is a sort of a sparse stream of spikes whenever sound comes into the sensor. And so our interest is to take the spikes coming from the different sensors and then to find bio-inspired energy efficient networks, because we're very much influenced by the brain. And because our eventual goal is to also implement these networks on either an embedded system that is low power so that you can deploy them for edge applications. And then to use this type of algorithms to solve some tasks that's suitable for the spiking sensors. And so I see by now there are many presentations on the dynamic vision sensor. So I'm just going to touch briefly more on the circuit side. And so here you see a piece of the silicon retina and it has these different classes of cells, right? So here's the photoreceptor that first receives the light coming into the eye, and then the bipolar cells that detect changes, and then the ganglion cells that look for constant brightness changes, right? So they send on the on and off spikes. And so the circuits or transistors that you see in the DVS pixels capture basically the functionality of these three classes of cells. And so this is one of the two major pathways of the biological retina, and it leads to this kind of video, which I'm just going to show briefly, just so that you can see what I'm talking about. So from the Davis, as you can see from the different talks, that you get both the frames, which is sort of our abstraction of the second primary pathway of the silicon retina, and then the DBS that captures transient changes. And so the frames, of course, give you like a picture, but then the transient pathway or the DBS output gives you the very precise timing that you get when you see changes in the scene. And so I'm going to go and explain more about the biological cochlea and the silicon cochlea, because this is the other modality that we're using in the fusion. And so I start off by showing a little bit of how the biological cochlea works. And so here's our ear here, where the sound coming in travels down the canal and then hits the eardrum. And so if you come down over here, you can see that the vibration of the eardrum causes the bones in the middle ear to vibrate. And the last one pushes onto this snail-like organ, which is called the cochlea. And if you could unroll it, then you'll see that it's basically a fluid chamber, and it's saying the fluid chamber is a piece of membrane that's shaped in a way so that it's going to pick up different frequencies of the sound. And so here's a simulation of what happens when you play a 6 kilohertz sinusoid. And you can see that when you play the sound, it sets up a traveling wave that leads to a particular place along the membrane.
Shih-Chii, can I interrupt you for a second? Your mouse is waving around in a random way. It not correlated with what you're saying. Yeah, can you point to what you're saying, talking about? The mouse seems to be lagging behind by seconds, many seconds.
Oh yeah, you're right.
Yeah, your mouse is waving in a very random way. It's disturbing. Yeah, maybe turn on the laser pointer.
Yeah,
I don't know why it's waving around in this random way. Okay, go ahead and turn on the laser. Yeah, there's a different mouse. Do you guys see that?
Strange.
The zoom button.
Okay. Now it's very possible that when I play a video, I have to go back to the normal mouse, because I see sometimes it doesn't work with this laser pointer. Okay, so it sets up this traveling wave, and there's different places along the membrane that would be displaced the most depending on the frequency of the sound. So you can see here for the 6 kilohertz signal that this particular place along the membrane is displaced the most. And so you can basically then present a whole sweep of frequencies and then look at the maximum displacement of the membrane for the different places along the membrane itself. And so here is what you get when you go from the base. And so if you're very close to the base, 13 millimeters from the base, you can see that you are very sensitive to high frequencies. And as you go away from the base, then you're more sensitive to low frequencies. And so this is the transfer function that basically led off to the first electronic cochlea that was modeled by a set of bandpass filters. Now, of course, what you see so far is not something that represents spikes. And so where do the spikes come from? And so in reality, when you look at the simple picture, the reality is that it's a much complex structure in the cochlea. And so in this picture, you can see that here's the basilar membrane sitting here on the bottom. And the basilar membrane is made of about 3,000 stages. So basically it's going to run into the screen this way. And for each stage, you get an inner hair cell and 3 outer hair cells. And so basically when the membrane vibrates, then the hairs of the inner hair cell will then move to one direction or the other. And when it moves to one direction, then ions come in and causes the release of a chemical neurotransmitter, which then causes spikes to go out on the afferent axons. And so this is a very simple picture of what you would see if you play a sound that consists of 2 frequencies, a high frequency and a low frequency. And here again is the base of the basilar membrane going to the apex. And so coming out from the cochlea are the set of auditory nerve fibers. There are about 30,000 of them. And so if you play this sound, which has both a high frequency and low frequency, then you'll see that different fibers will produce spikes. Okay. And so now what I show you is basically a block diagram of what you get now in the spiking silicon cochlea, which we also call the dynamic audio sensor. And so it has 64 channels. It's a binaural cochlea. And so basically it's got 2 ears. And for each of the channels, you have the bandpass filter, right, which captures the functionality of the basilar membrane. And then we have a rectifier, which is carried out through an asynchronous delta modulator, and which gives you on and off spikes. Now in the actual cochlea, it's actually halfway rectified, but in this particular cochlea, it's designed so that it gives you both the on and off polarities. And what's nice about this particular design, which was done by Minhao Yang back in 2016, is that if you look across the 64 channels, you can see that the transfer functions are very well matched. And so this is really something very amazing for a mixed signal design. And now if you play a chirp, basically it means that it's a sound that's changing in frequency. And so here we play a sound that starts off at 6 hertz and then goes up to 21 kilohertz over 75 seconds. If you set the Q of the filter to 1, then what you see is there's a set of channels that first respond, and then as the frequency increases, then the next set of channels respond, and as you increase the frequency further and further, you can see now the lower number channels respond. Okay. And if you want to see how this thing looks like in time, so here again are the 64 channels. The preferred frequencies are shown here in the box. And so now so you can see with the laser, it doesn't work. Oh, okay, maybe that works.
You should just be able to hit the space bar too. Yeah.
Okay. Yeah, so we're going to change the frequency from 8 hertz up to 20 kilohertz or so, and you can see the different channels responding as the frequency of the signal increases. And so the next thing is, what can you do with the spikes? Of course, the first thing that you try is localization. And I think this is already shown by Toby in the talk yesterday. But the idea here is that if you want to know where a sound source is in the azimuth direction, basically, on the horizontal plane, then what you can do is you can take the spikes from the left and the right ear, and they're color coded here. So the blue are the spikes coming from the left, the red are the spikes coming from the right, And then you can look at the delta T difference between a spike in a channel with the corresponding channel of the other ear. And basically you can build like a histogram, which looks a bit like this. So here's a histogram of delta T's, where delta T is 0 in the middle and then plus minus 700 microseconds on the far right and left. Okay, I'm not going to play this video again because I want to get to the interesting bit, and you've already seen it. Oh, okay, all right. And so I'm going to now talk about a previous work where different groups have also tried to combine the spike outputs of these different modality sensors, right? And so this is work by Vincent Chen and Andre van Schaik, where they first put the a vision sensor. It's not the dynamic vision sensor, but it's a transient retina sensor that also puts out spikes. So you can see here in the front. It's mounted on this robot that's called the Koala. And then on the top of this sphere here, you can see on the sides, they place microphones which go to this Cochlea board which is a design that Andre and I did in the past. And then what they did was they put a speaker in the front facing the robot, and on top of the speaker, they put different LEDs. Right, and so the idea here is to, first of all, how did they use the output spikes of the two sensors together? So first is they learned to adapt the sound localization output to self-motion and visual feedback using adaptive ITD, interval time difference, based sound localization algorithm. So what it means is basically if the delta T doesn't match the direction of the sound source, and you can tell what the direction of the sound source is from the LED, then you can use this error signal basically to reweigh the influence of an ITD that's computed from a particular channel, right? And the other thing is they also dealt with a simple source binding problem. So with this, they can look at the effectiveness of matching an audio event with a corresponding visual event based on your onset time. And so what they did was they mounted 3 LEDs, and so two LEDs blink at different frequencies, and they're not synchronized with the presentation of the audio input. And then the third LED is matched up with it. And so they wanted to see whether they could detect the third LED based on synchronization between the audio and the visual event. Okay, so I think this is probably the very first report of how they've combined the two sensors together. And so we've done something which is not truly like sensor fusion, but it's more that one modality drives another. And so this is a steam stitching work with DBS and DES done by Philip Klein and Jörg Conrad. Some of you might know, he builds very lovely robots. And so Jörg Conrad's group built this lovely pentil system where they have a motor that drives the neck. And then they have here the 2 microphones, they have 2 DBS cameras. They're mounted on their own pentil system. And so for the head, you also have your own pentil system. And all the commands are presented to a microcontroller board. And so the idea here is that we wanted to use the sound to drive where the eyes are looking at, right? And the other thing is we do something called scene stitching. And what that means is that we basically take the output of 1 DBS, which is only 128 by 128 pixels. And then we use it basically to paint out a scene that's equivalent to 628 by 418 pixels by basically moving the neck around, okay? And also the head. Okay. And so this is what we use to basically use. So now what we do is we use the sound source to determine where you want to paint. And so we call this selective visual attention using DES for scene stitching. And so here you can see that robot head again. So there are 2 sound sources. So here we have a speaker in the middle playing a sound at 500 hertz. And then there's a human who's going to talk, and they're going to talk in 4 different possible positions, right? And so the sound basically comes on and off for about 30 seconds. And what you can get from the output of the DBS is that, first of all, you can see the speakers over here in the middle. And then when you stand in one position and you talk for 30 seconds, you can see it paints the person in that position. And you basically, the rest of the scene is blank. And then if that person moves in 30 seconds and then starts talking again, then you paint the scene around there. And then and so on and so on, right? So now you move to third and fourth position. Okay, so this is one example of how we use the spikes from the two modalities together. And then we had this idea that we should do lip reading, because lip reading naturally is a task where you can use both audio and visual cues, right? And so we attempted to do this back in the Telluride Neuromorphic workshop in 2015, together with Sumajit Mandal and Arina Basu. And we tried to collect a data set of 6 speakers using Davis and Dest. And just to give an idea of what we collected back, ooh, no, it doesn't work. Sorry, it doesn't work with the pointer. Yeah, so we collected data from the retina, the cochlea, but we also collected the frames and also the microphone samples, right? So that eventually we can use all 4 types of inputs together. And we only managed to get to the part where you can see here how we tried to filter out all the spikes over here so that we can figure out where the mouth is, right? And so we managed to get to a part where we can actually identify where the mouth is. You see that when somebody's speaking, suddenly you get like a burst of spikes, right? And so we had an algorithm that basically extracted articulatory parameters or mouth shapes from DBS data. Okay, and then from then on, we moved to, I guess, the topic of this talk, which was classification using a deep belief network. And so this is work that was headed up or speared by Peter O'Connor, who was a master student at the time, together with Danny Neal, also a master student, Toby, and also Michael Pfeiffer. And remember, this is back in 2013. So back then, the machine learning algorithms were not as impressive, and also they were a lot different from what we do nowadays. And so at the time, remember, Jeffrey Hinton was pushing this deep belief networks, and this networks are trained in an unsupervised manner. And so what we wanted to do was to take the spikes from the retina and the cochlea, pass it to a deep belief network to produce some label. So basically train on some classification task, right? And so this deep belief network here is a probabilistic frame-based machine learning model, and it consists of stacks of these restricted Boltzmann machines. And each of these neurons are actually sigma neurons, and they're trained using unsupervised learning. And so what you want is to extract more abstract representations as you go up the hierarchy of the network. And so we trained it on the 16,000 handwritten digits from MNIST, right? And so you can see the architecture over here, right? So here's the visual input from MNIST, it's only 28 squared. And then it goes to
Shih-Chii, can you turn on the laser again? You have a recorded mouse that's confusing. Yeah, there you go.
Yeah, thanks. Yeah, I tried to remember to go back again after I played the video. Okay, and then it goes up to visual abstraction layer of 500 neurons, and then another abstraction layer of 500 neurons, and then to the label layer with 10 neurons representing the 10 digits, right? And then we can also come in with the audio input with a layer of 100 neurons that basically goes up to this abstraction layer that merges the two features together, the visual and audio features together. And then because the deep belief network, you can actually go the other way. You can actually stimulate the visual abstraction layer and then see what the input was that was coming in. And so so remember, we had this lip reading thing in mind, but at the time, of course, we didn't have the lip reading thing. So basically we had the MNIST, but we don't have like the sound from digits, right? Somebody speaking the digits. And so what we did instead was we associate each digit with one logarithmically distributed audio tone with some frequency, right? And then the training process uses unsupervised learning to group the visual features with the audio input. And then this fused visual audio representation is then trained with the digit label. And so here you see the function of each of these blocks again. So we have the spiking sensor going to visual layer, spiking audio, network going into the merge layer, both of this going to merge layer, going to label layer. And then of course, this is spiking sensors. So here, we just want to show you what you would see in each of this, the outputs of the different neurons as you present a 4. And then you see the kind of the spike rate of the neurons in this layer. what the input was when you try to reconstruct backwards. And yeah, and then you can see it's kind of hard to read what's going on in here. And then finally, there are 10 neurons for the 10 labels. So it's 0, 1, 2, 3, 4 this way, and then 5, 6, 7, 8, 9 that way. So I'm telling you that because we're going to see a video next. Okay, so here's the video. So what you see here is the output of the DBS, and then here is the output of the DAS, right? So here's the different frequency channels, and then, you know, depending on the frequency of the sound coming in, different rows will light up. And then you get here the output of the visual layer, the merge layer. I mean, basically, I think you can just kind of ignore this different panels. What's interesting would be the output of the visual layer, the reconstructed input, and then also the label, right? Because remember, it's 0, 1, 2, 3, 4, 5, 6,
Okay,
7, 8,
go ahead
9.
and play it, Shih-Chii. We're out of time almost.
Okay, so this is actually going straight to the fusion to make things faster. So this is an incomplete 5. It could be a 3 also. And because we've trained this particular tone to go with a 5, then if I present the incomplete 5 with the tone, then I get an actual 5, but I can turn it into a 3, right? So here we take away the tone, you get a 3, and here we play the tone again, a different tone. You can see the higher channels respond, then we got a 3, right? Then we go to a different tone, then we made a 5. So basically we can flip it back and forth, okay, depending on what you get from the audio. All right, so this never runs on the CPU. We want to transfer it, of course, to hardware as usual. And so we transfer it to a FPGA platform. It's a Spartan 6. And Danny Newell was the one who did the work on the spiking DBN for this FPGA platform. It's called Minitaur. And it's a great name. And then Ilya Kiselev then basically picked up the work after that and made it even better, right? And so there's some interesting bits about implementing a spiking neural network on a hardware platform. There's computational difference. So first, the neurons are stateful. So the stateful representation amortizes computational costs over time. Second, we're dealing with spikes. So that means you're going to get bursts of spikes. And this kind of burstful workloads require intelligent scheduling. And then one thing that's nice is that you can get a low latency to first output. And because it's sparse activation, then you can actually cache the activations in a smart way, right? So we can discuss the Minitaur architecture during the Q&A, but this is just to show that we mapped it, this whole thing to the Minitaur, and just going straight to the demo, just to show you that it does work. So here we go. We have the DBS, a loudspeaker, Minitaur sitting over here, silicon cochlea. This is the digit that's shown to the DBS. And then the recognized digit is shown in this display here, okay? So first we do video only, right? So you have to see whether this matches this, right? So 3, 3, 6, 6. Then we did it only with audio, but we purposely added noise so that it would not work as well. So anyway, it will make mistakes. And then now it's to show that if you combine both of them, then it would give the correct answer, okay? Yeah, so here's the summary. So fusing multimodal events can lead to better accuracy. We demonstrated on the real-time sensor fusion platform using a DBN with DBS and DAS. You can see the spike rates are quite low. There are like 1,000 spikes per second. Latency is also quite fast, 2 milliseconds. It's running on Minitaur, which is about 1.5 watts. And then basically we want to also push this idea of event-driven computation, because this kind of computation scales the workload with input activity. There's something here about the cache of Minitaur, which I won't discuss. And finally, this event-driven computation progressively refines the stateful representation. and best paired with a low latency implementation so that other systems can use, what you partially compute. Right? It's not done frame by frame. And finally, to acknowledge the census group, so here's Danny Neal, who's graduated a long time ago now. Ilya is still with us, doing some cool stuff. And Toby, and then thanks to funding agencies and to all of you for listening. And are there any questions?
Okay, thank you. Okay, so we still have like 5 minutes left out of 10 minutes for any questions. Thank you, Shih-Chii. It's really cool to see this early and broad neuromorphic type of sensor fusion. It's quite a departure from the recent trend to use these giant DNNs. The Minitaur SNN accelerator is still activity driven, right? So.
Yeah.
Okay, so inside the layers, the Boltzmann machine layers, the events don't arrive collapsed. They arrive on a first come first served basis.
Yeah, the timestamps are recorded. Okay. Yeah, and it's event driven. So even though it's run on a synchronous platform, you wait till you get the events or the spikes, right? And you have the timestamp, so you can figure out how to update the memory potential of each neuron.
Okay.
Yeah.
And the neurons that you use on the RBM, they are also like leaf neurons or like.
Yeah, the leaf neurons.
Okay.
Yeah, you can see here in the Minitaur core, this architecture. Yeah, you can see the input summation, the DSP block is for summation and DSP block for the memory decay. Right. And then you can have exponential decay also if you like.
I mean, what Minitaur was really about is that we wanted to explore whether it was possible to cache weights and states of active neurons in a spiking neural network to avoid repeated DDR memory reading. Because the big weakness of SNNs is that they're asynchronous. So they suck when you have to use DRAM, where DRAM only works well when you access it synchronously in big burst reads. And here we wanted to see whether we could use local SRAM cache to cache this network information to avoid this memory. And it's the only architecture that does this, as far as I know. But it was still very limited in its actual performance, like to a few tens of thousands of events per second. Very, very low. But so we didn't go back to it since then. This idea.
Okay.
Yeah, but it's still worth looking back in hindsight,
Would
right?
be, interesting given the current FPGAs that.
I don't know. Do you agree, Shih-Chii? I mean, it's still worth taking a look at. But in the meantime, we got away from SNNs because of this big memory bottleneck problem. Because if you want to scale them, you have to use DRAM, right? You can't fit everything on a chip. Anyway, we have to take a break.
Yeah.
Yeah. So maybe we take a 5-minute break. Now it's 30, so we can come at 35.
35. Okay. All right. Thanks.